You know, the Westinghouse AP1000 was supposed to be a total game changer for nuclear power. It was this revolutionary reactor design that promised a whole new era of safer, cheaper, and faster-to-build energy. But its story, especially here in the United States, turned into one of the biggest cautionary tales in the history of modern construction. So, let's get into it.
This is the number that tells you pretty much everything you need to know. Over $30 billion.
And that was the final eye-watering bill for just 2 new reactors at the Vogtle nuclear plant down in Georgia. It made it the most expensive power plant ever built anywhere on Earth.
But here's the thing. It absolutely positively was not supposed to go down like this, because this was the original budget.
Yeah, a massive cap is putting it mildly, right? The final cost more than doubled, and the whole thing finished years and years behind schedule.
So that's the big question we're tackling here. How does something with so much promise go so catastrophically wrong? And, maybe more importantly, what can we learn from it so this never ever happens again?
To really understand the failure, you first have to understand the promise. See, the AP1000 wasn't just another reactor. It was specifically designed to solve the very problems that had plagued nuclear construction for decades.
Okay, so at its heart, the AP1000 is what's called a pressurized water reactor. Now, I know you're looking at a lot of technical stuff on this slide, but don't worry about the jargon. The key takeaway here is its design philosophy, which was all about simplicity and something called passive safety.
And this is where it gets really cool. All these features were meant to work together. Passive safety is the big one. It means the reactor can use natural forces, like gravity and water circulation to cool itself down. No pumps, no outside power, no human needed for 72 hours. Fewer parts meant less to build and less to break. But the real game changer was supposed to be modular construction. The idea was brilliant. Build huge chunks of the plant in a factory, ship them to the site, and then just click them together like giant high-tech Legos. This was supposed to finally make building nuclear plants predictable and affordable. But, well, that beautiful promise ran headfirst into a brick wall of reality. And the story played out completely differently on opposite sides of the world.
This table just lays it all out crystal clear. Look at the U.S. projects. Vogtle took almost 15 years and cost over $30 billion. V.C. Summer, they just gave up after sinking $9 billion into it. Now, look at China. 4 AP1000s, all built, all operational, for a fraction of the cost. So what does that tell you? It tells you the technology could be built. The problem wasn't the reactor design itself, it was the execution.
All right, so let's put on our detective hats and really dissect what happened in the US. Why did a project with this much potential just fall apart so spectacularly?
It really boils down to 3 huge interconnected problems that all fed off each other. First, the design wasn't actually finished when they started building. Second, the quality control for those factory-built modules completely collapsed. And third, the financial structure of the whole deal was just too fragile to survive the first 2 disasters.
Let's start with design maturity. Now, this is like rule number 1 for any giant construction project. You have to finish the blueprints, 100%, before you pour the first drop of concrete. If you don't, every single change you make on paper creates this massive ripple effect of delays and rework out in the field.
And how do we know the design wasn't frozen? Well, this number says it all. Over 180. That's how many license amendment requests were filed for Vogtle. Every single one of those was a formal change to the design after it was supposed to be final. The design was anything but frozen.
This quote just nails it. The entire regulatory system was set up to prevent this exact thing from happening, and it happened anyway. They were basically designing the plane while they were flying it, which, let me tell you, is an absolute recipe for disaster in nuclear construction.
Next up, the quality collapse. Remember that whole promise of perfect factory-built modules? Yeah, about that. The reality was a total nightmare. The factory in Lake Charles was churning out modules with so many welding defects that the Vogtle site had to build a massive dedicated facility just to fix or completely remake the parts. It turned their biggest advantage into their biggest bottleneck.
And that brings us to the final nail in the coffin, the contract. The utilities used a fixed-price deal, trying to push all the financial risk onto the builder, Westinghouse. But the costs from the design changes and the quality problems just became so massive that they completely overwhelmed Westinghouse, forcing them into bankruptcy. And here's the kicker. That bankruptcy made the fixed-price contract totally void. All that risk, all those billions in future costs, came flying right back to the utilities.
For the owners of V.C. Summer, the new price was just too much to swallow, and they pulled the plug.
But okay, so while all this chaos was unfolding in the US, something totally different was happening in China. And this is what proves the problem wasn't the tech, it was the entire ecosystem it was being built in.
So what was their secret sauce? Well, it wasn't just one thing. They had experienced, state-backed teams. They used a fleet-based approach, which is a fancy way of saying that the lessons they learned on the first reactor were immediately used to make the next one better. Their whole system could handle technical problems without the main contractor going bankrupt. They learned fast, they adopted, and they even created their own version of the design with their own supply chain. It was a program, not just a project.
Look, the failure of the U.S. projects was an unbelievable financial disaster, no question. But it did produce a mountain of invaluable data. So the really important question now is, how can we use these incredibly expensive, hard-won lessons to de-risk the next generation of nuclear power plants?
What the data tells us is that nuclear project costs have what analysts call a long tail. What that means is, yeah, most projects will go over budget by a bit, but there's a very real, statistically significant chance of a catastrophic Vogtle-level overrun. You have to assume this risk exists and manage it from day one.
And this is why that risk is an absolute deal-breaker for investors. A major cost overrun doesn't just lower your profit, it completely obliterates the entire economic case for the project. It's why private money is so scared of these projects. Unless you can prove you've tamed that risk, the numbers just don't work.
So, from all this painful experience, a really clear playbook starts to emerge. 1. A strict, non-negotiable design freeze, period. 2. Use integrated contracts where everyone, the owner, the builder, the supplier, shares in the risk and the reward. You're all on the same team. 3. Test and qualify every single piece of your supply chain before they start work. 4. Replicate, don't reinvent. Build copies of a plant that's already finished and working. And finally, 5. Work with regulators to make their oversight smarter and more focused on what really matters.
In the end, the story of the AP1000 teaches us that brilliant engineering, it's just not enough. The real challenge isn't just designing a better reactor, it's mastering the insane complexity of actually building it. So the big question now is, has the industry, have investors and governments truly learned these multi-billion-dollar lessons? We'll have to wait and see.